So today I'll start by reviewing the light conformalism that we discussed last lecture, and I'll make this remark about parity and inversion that I skipped last lecture. Then I'll remind you how we did compute the 2 and 3 point functions, and I'll this time compute specifically the 4 point function for scalars using the light conformalism. And in the midst of the calculation of this 4 point function, we're going to have to discuss what is known as conformal invariants. Conformal invariants could have been discussed earlier when we discussed what are conformal transformations in general, but I just pushed them back here when they actually appear, when they are actually needed. Okay, so to remind you, the light conformalism, I'll just put the results here. I'm not going to do the computation this time. The idea was just to understand conformal transformations of physical space as rotations on a d+2 dimensional space that we call the embedding space. And sorry about that. The physical space should be somewhere on this embedding space, and our task is to find where it is. Okay? And we found that the answer to this question was we introduced two coordinates, xd plus 1, which was a space-like coordinate, spatial coordinate, and xd plus 2, which was a time coordinate. And then from this we constructed the line coordinates, x plus, x minus, by this linear combination. And the reason we construct these line coordinates with these coordinates x d plus 1, x d plus 2 was because these are precisely the coordinates that we want to eliminate. They are the two unphysical coordinates that we introduced in order to discuss this light conformalism. And the reason we use this light conformalism is because the answer to that question, where the physical space lies in this embedded space, that we found, at least the simplest choice, was the light cone made by these two extra coordinates. So this is the light cone, this is the x plus direction, this is the x minus direction. Physical space is represented by this axis, x nu here. Just remind the coordinates on the embedding space I call the x capital M, the first mu coordinates, just the physical space coordinates, and then we have in this light coordinate we have x minus and x plus here. Okay, and we found that the physical space was this constant section here that we chose at 1, something like this. Physical space was represented by x minus equals x squared. This capital X mu is just the physical space x mu. X squared is x squared 1. Okay, this was the answer we found. And there was a discussion, and there's actually an erratum here. So just make a solution here. I just got a bit ahead of myself, and I told you that the light cone is the only invariant surface. Of course, it is not. That is, you have the light cone, you have these two-sheet hyperbola and this one-sheet hyperbola. If you have more coordinates, then you just rotate this, so this guy is connected. So this is the one-sheet hyperbola, but these guys are disconnected, so this is the two-sheet hyperbola. And so this surface, the one-sheet hyperbola, the two-sheet hyperbola, and the Lycon coordinates are the invariant surfaces, and we just, and I got a bit ahead of myself and told you that the Lycon was the only one. Of course it is not, but the reason for choosing the Lycon is because this, whatever surface here I pick, will only eliminate one coordinate, and we must still get rid of another coordinate. Okay, picking one of these will eliminate x minus, but we still have to eliminate x plus. And we know that whatever the second constraint is, we'll just take this surface, whatever we choose, and select as slice. Okay? And the thing is, the only invariant surfaces are these ones. Okay? So no slices of this surface are invariant under the rotations. So since we cannot find any slice in these invariant surfaces, we do the next best thing we can do. We just introduce what we call the projective constraint, which is basically saying that, okay, even if I cannot find any rotational invariant slice of any of these surfaces, I do the next best thing, that is, I'll relate different points on this surface to each other and say they are physically equivalent. That is basically the same idea as gauge invariance. Okay, we have different points furnishing the same physical quantity. Okay, and to actually do this, to implement this idea, we need some kind of relation, and that is where the Lycon differs from these hyperbolas here. Because in the Lycon we discussed that is the theory that says that any two new vectors are orthogonal if and only if they are proportional to each other. And so, for that, remind you, if xm is a new vector, then introduce this projective constraint, because again, if it is a new vector, this is going to be 0. So if I start with a point here on this section, okay, which I'm calling physical space, and I do a rotation or a transformation, then I'll escape the section, so to speak. But whatever the points I find myself, there is a light ray from the origin passing along this point. There's only one light ray, and associated to this light ray there is this constant factor here, lambda, that projects me back into the section. Okay, so this unique solution. Okay, so there are many associated to the same physical space point. There are like infinity of other points lying along the same light ray. Okay, so this is just like gauge fixing. And again, this construction was a choice. There might be other ways to embed physical space into this embedding space, but this is, as far as I know, the simplest one. Also, in choosing the x plus constraint, we made a further choice that we remind ourselves that we're interested in studying conformally flat theories. So, in order to do that, the solution was to take x plus as a constant, and since it can be any constant, just took it to be 1. Okay, but again, even for conformally flat spaces, you could probably make another choice, but you have to solve a differential equation to see what are the allowed solutions and so on. Okay, so this is the simplest. It is a choice, but it's the simplest, and it just suits our interests. Okay. Any question about this? This was past lecture. No? Can I erase the errata? And so, because I'm just about to need it, I know it's right here. Okay? This is also called the point kind of section. Okay, this choice section. we shall just abbreviate for ES. That you can either understand as point section of physical space. It's just for coincidence. So, and past lecture I just skipped this remark about parity inversion that is made in this light conformalism because I wanted to give you a flavor, a taste of how to compute correlation functions. And this is a quick one. I'll actually start with inversion. So I'll write it there. Inversion on physical space we discussed in the second lecture, I guess. Whatever it is, I'll remind you that it takes x mu to x mu I for inversion. That is simply x mu divided by its modulus squared. Okay, this is the inversion discussed in physical space. Okay. And we're interested to see how to reproduce this from an embedded space. And I'm just going to give you the answer and show that it is actually true. And the answer is this can be achieved simply by exchanging, this is on physical space, and embedding, ES stands for embedded space. This can be achieved by exchanging x plus with x minus. And the reason is, let's do this explicitly. Here, okay, on the point. Okay. Let's do this step by step. We have x mu, x plus, x minus. Then restricting this to the point intersection or physical space, this becomes x mu 1, right? You get from here 1, and then x squared. Now the thing is, look at the structure of the point intersection. It has a position vector, then it has the modulus squared of the position vector, then it has 1. Okay? In order to recover this structure here, we have to rescale, we have to pull out this factor of x squared. So I'm just going to drop it, it doesn't matter. So this becomes x mu under x squared 1 over x squared 1. Okay? So what happened here? We had a position vector, and now in its place we have its inverse. Okay? So here in the first component we have what we actually know that represents inversion on physical space. Then we have the modulus square of this vector. Okay? The numerator we just have x squared, and the numerator have x to the 4th, so end up with 1 over x squared. And then the last component, we also have 1. Okay? So this is the reason you see that inversion on physical space can be implemented simply by exchanging x plus with x minus. Okay? So further on to that, let's discuss now inversion. Oh, sorry, parity.
ES is Euclidean.
It's it's an embedded space.
Embedded.
Okay. This is how we implement inversion. This is what you know. It is an inversion of physical space. Okay. And this is what inversions are in embedded space. Okay. They're implemented by exchanging the two extra coordinates. Okay. Any more questions? No. Okay. So parity. What is parity? This parity is just the usual Poincare parity. Okay? The parity that is present on the Poincare group. Okay. That is, you just take, you have separated. If you have even spatial dimensions, then you just invert all spatial dimensions. If you have odd spatial dimensions, you just invert one of them. Okay? And by inverted, if you have even spatial dimensions, and you take x minus x. You're just inverting the sense with the minus. The spatial coordinates, if you have what? Spatial dimensions, then you just take one of them, say the first one. And the reason is, if you don't remember, if you do this for odd, it's the other way around. It's the other way around. Now, and the reason, if you do this, invert all spatial directions, and you have even space direction, and this you see is just a rotation. Okay, you can see it easily on the plane. If you have this point, then minus this point like somewhere here, but this is just a rotation. Okay, this is true for any even spatial dimensions. So inversion on an even dimensional, even in a space with even spatial dimensions, you just invert one of the coordinates and bring this guy here, for example. Okay. But just to make this more uniform, just modify this and say okay, it works the same way. Okay. Parity must have determinant -1. Okay, it is not connected to the identity. Okay, so whether if I have odd spatial dimensions, whether I invert all spatial dimensions, or if I invert just one, just like in the even dimension space case, then it is the same. What happens is to relate these two transformations, then we just invert one coordinate, and then by a rotation, we can bring the other coordinates to be negative by the same argument that I gave you here in the even dimension space. Was it too fast? Is it clear?
So if you invert in the odd dimension, if you invert one coordinate, you can rotate and invert all, get all orders inverted?
Yeah, this is what I usually call parity. Say if you have a physical space, 1 plus 3, okay, you have 3 spatial dimensions, then this is what we call parity. Okay, we invert everything, all spatial dimensions. But another way of doing this would be invert, just pick one of them, any one of them, invert this one, and then do rotations in the other two that you left untouched. You can do a rotation such that this become all negative. Okay?
Oh, okay.
Okay.
Okay. Because we invert the plane x1, the plane which
yeah, we invert x, take x minus x, and do a rotation. Yeah,
okay.
Exactly. Okay? And what I'm saying, telling you this because you have a connection here with inversion, is here I give you the condition for, in terms of these light coordinates, x plus and x minus. But, okay, so back to inversion. I wrote them here, right? Okay, here it is. If I exchange x plus and x minus, I can achieve this simply by taking x d plus 1 to minus x d plus 1. And then the overall minus factor doesn't matter. Okay? So this is equivalent to taking x d plus 1 to minus x d plus 1. Okay? And remember, the x d plus 1 is a spatial coordinate. Okay, so it is. It doesn't matter if the total, if the embedded space has even or odd dimensional space. This is kind of a parity transformation. Okay? If you have even dimensional space, then this is just exactly parity, and if it is odd dimensional, has odd spatial dimensions, then you can just do a rotation to get what you actually call parity. Okay? And the thing is, the relation here that I discussed is just a rotation. Okay? But our embedded space, we're sitting on the icon, which is a surface that is invariant on the rotations. Okay? So, what is the conclusion here? If you have a field theory, conformal conformal field theory, which is invariant under inversion. Then it must also be invariant under parity. Okay, because on embedded space, on the light cone or on the point section, they are related. Okay, this step, they are related by a rotation, which leaves the point section invariant. In that sense of the gauge fix and all. Okay, this is a claim that I made in the first lecture, I guess, or the second lecture, that if you have a CFT that has inversion, invariance, then it also has parity invariance and vice versa. It is just a 5-minute proof on the light conformalism. Okay, so that's what I wanted to show you. But again, remember that since these two transformations are not connected to the identity, generic CFT does not have to be invariant under any of these transformations. Okay? Any questions? So we're going to move to the correlation functions. 2, 3, and 4 point correlates of scalars. Can I raise this backward? Not? No? Yeah. So, scalar. Okay. The idea is to compute correlators on embedding space, or just since I already used it on embedding space, and project into physical space. Okay, and this task is easy on embedded space because you just have to care about rotational invariance. Okay, so if I take two scalars at point phi1 at point x1 and phi2 at point x2. Okay, they are different scalars in principle at two different points. Then the most general expression you can have for that is what is invariance is something like this. Plus something that is proportional to say x squared, and something that is x1 squared, something that is proportional to x2 squared, for example. Okay? This is on embedded space, whatever on embedded space. And first of all, the reason I put this guy downwards is because, of course, you have also the physical requirement that correlation should die as you increase the distance, so it should be either 4 or something like that. Okay.
That is to the power of delta?
Delta.
The scaling. The scaling.
Yeah, but it's not to be the scale, but we don't know this yet.
Okay.
Actually, we know because I skipped something on the review on the light conformalism. That I should have reminded you of that. We discussed the light conformalism, but in this review, did not remind you what happens to fields. So if I have a embedded space field at point x, then again, on the hypothesis is that if I restrict this field to the point section, I will identify this with the field in principle to be denoted by a different letter. This will coincide to the field on physical space. Okay, this is an hypothesis. Okay, I take the field on the embedded space, restrict it to the point section, and whatever I get, I will identify with the field in my physical space. Okay, this is an hypothesis, just a formulation. And remember that in the point section you must rescale because it's not invariant. Okay, there is a gauge fixing. So I have to tell you how this behaves, that is, how this guy behaves on this rescale. And this is another hypothesis that is the Dolores transformation. If I'm in the point section, then Dolores transformation, I will end up in a point x prime that is related to this point here by rescaling. Okay? And the hypothesis is that this is all the point section. Oh, sorry, this icon, this is back in the point section. And then the hypothesis is that the guy is just a kind of a scaling behavior. Okay? And then this condition throws back here, you'll get that first guy back. Okay? I'm already supposing that delta has to be positive. Implicitly. Okay? So this is where the first guy comes from, and then I can have whatever here that is proportional to x1 squared and x2 squared. But now I come here and restrict this guy to the point intersection. So the point intersection lies on the line. So this, whatever these contributions are, they will just die. Okay? So okay, I could have also a constant here. Whatever it is, I get this. Okay, the point intersection. And remind you that we discussed that the scalar product on embedded space. This is embedded space. This is just x1 nu x1 nu minus half if I use the like coordinates. Okay, this is an embedded space. And then if I restrict this further to physical space, then the x minus are just x squared, x nu squared, and x plus is just 1. So this reduces. This is a result we got last lecture. Minus 1/2 x1 minus x2 squared. Okay, this is what you to just restricted further to the point intersection. Okay, and so this is the last simplification must go here. So we end up with so since I've already the point intersection, just call this the lowercase x1, x2, and I'll drop this ps here. And here we get, because of this minus half factor, we get minus 2, C12, but this is just an overall normalization factor that I can normalize to anything I want, so I will normalize it to be 1, okay? It is a choice. So I end up with, and this guy becomes x1 minus x2, and because of that 2 here, the power of 2, I end up with 2 delta here. Okay? So this is the correlator of any two scalar fields in physical space. Okay. The any part that I said, I will add some observation to this at the end. Okay. But one thing to notice that can get that you might not notice when doing compute correlation functions through the formula, like conformalism, is that this only works if phi1, in principle phi1 can have scaling dimension delta 1, and phi2 can have another scaling dimension delta 2. Okay? But in order to construct this Lorentz invariant term here, I must have that these two guys are equal. Okay? Otherwise, I cannot construct a Lorentz invariance if I have a delta 1 here, delta 2 here, and they are different. Okay? So there is a further condition. Because of this, there is a further condition that you need to write this. The 2-point function of these scalars vanish if their scaling dimension is different. Okay? The scalar fields can be different, but their scaling dimension must be the same. They are not, the 2-point function vanishes. Okay? Solely on grounds of conform invariance. If they are equal, then the correlator is given by this form. And where this delta is just shorthand. Okay? So this one was easy. There is any question? Okay. No? Well, let's do the 3-point function now. Can I erase this? So we just play the same game. You write the most general 3-point correlator in a embedded space, then we go straight to the Poincaré section. Let's see what happens this time. So on the embedded space, I have phi1, capital X1, phi2, capital X2.
Sorry, but why did the last term in the first one vanish?
These two guys?
Yes.
Okay, this is on embedded space. Okay, this is on embedded space.
Yes.
Okay.
So
This is on the Poincaré section. Okay. So the Poincaré section lies on the line. Okay, so these points x1 and x2 they lie on the line. So the x1 squared and x2 squared must vanish. Okay. Any more questions? No?
I mean, the only word, actually, I mean, but the formalism is good for higher correlation functions, no? Because here the only word would be really to show that the 2-point correlation function was for scalars with different scaling dimension is 0. Because the other ways, things just follow immediately also in the other formulas, no?
On the actually taking the correlation functions, make a conformal transformation,
Yes.
and impose the constraint. Yeah, okay. For the amount of work through the like conformals or through the pedestrian way is just basically the same. But as you go to higher point functions, then this becomes more powerful. And especially if you do correlation functions of spinning particles or spinning fields. But in this class, I want to discuss the scalars. This spinning correlates I might discuss in another lecture when I turn to the energy momentum tensor. Okay? Because every CFT will have an energy momentum tensor, and the energy momentum tensor is one of the most important objects of a CFT. Okay? And it is a spin-2 object. But I just want to get to I want to discuss this, then I want to get to the structure of the Hilbert space in more detail, and discuss the operator state correspondence, discuss the OPE, and all the things, which are the most fun things, I guess. edit thing. And then we're gonna go back a little bit and discuss the energy momentum tensor. Mainly because the energy momentum tensor is also involved in the more advanced applications. Okay, the questions as to whether scaling invariance implies conformal invariance and so on. You usually have to look into the energy momentum tensor. So I just trying to push this to later lectures. Okay. Any more comments? Questions? No? Okay. So let's continue this. And again, I can have in principle 3 different scalar fields, 1, 2, 3. They sit at 3 different points. This is on embedded space. And then I already dropped these terms here. Okay, it's not right there. Because when I restrict to the point section, it will just drop anyway. So the only surviving part would be something like this. Okay, I can make a scalar product between x1 and x2 with a coefficient alpha 1, 2, 3 here. Then I can make a scalar product between these 2 guys with another coefficient alpha 2, 3, 1. And then I can make a scalar product between x1 and x3 with yet again another power alpha 3, 1, 2. Okay, and the coefficient C1, 2, 3 here. Okay. Let me just see if this is the convention actually using here. Like this. So then we restrict to the point section. Okay, so all these scalar products become something like this, and all the factors of -1/2 I'll just reabsorb on this constant. Okay, so we still have a C1, 2, 3 where we're plugging all those factors of -1/2, and here on the denominator I end up with, and I'll introduce this notation. I'll call x1, 2. Here, x ij will be xy minus xj. Okay, just a shorthand notation. So this scalar product will furnish x1, 2, 2 alpha 1, 2, 3, x2, 3, 2 alpha 2, 3, 1, and then x3, 1, 2 alpha 3, 1, 2. Okay, now we need to fix, if we can, these 3 powers here. And the way to do is this correlator must have scaling invariance. Okay, so say phi1 has scaling dimension delta 1, phi2 has scaling dimension delta 2, and phi3 has scaling dimension delta 3. Okay, they can be different in principle. The thing is, in this denominator on the right hand side, I have 2 sources of x1, this guy and this guy. Okay, and their powers are 2 alpha 1, 2, 3 plus 2 alpha 3, 1, 2. Okay, these powers must match delta 1. Okay. If I do a scaling, I have to say a factor of lambda, so I end up with a lambda to the power of minus delta 1 that should be reproduced in this side. Okay, with the powers that take that have.
Delta 1 or 2 delta 1?
Actually, I missed.
No, sorry.
No, it's probably.
No, I think you're right.
A bit, no, because it's usually
No, I think, sorry, I think.
Okay, but there might be something of convention here because people came
Yeah.
to because let's do the computation, then we'll see. Okay, because I have the right answer here. Okay. Let's go with this one.
Yeah. Multiply by that one.
This?
Yeah.
Okay, I mean, so say I have square roots, okay? And say I just scale this guy, okay? Scaling simply implies that this must be, okay? This is on the left hand side. So in the right hand side, I do the same thing here and here, because these are the only two guys that have x1. Then I must end up with the power of minus alpha. Okay. Then I do this for x2 and x3. So x2 I have 2 alpha 2 3 1 plus 2 alpha 1 2 3 equals delta 2, and then for x3 I have this and this, so it is 2 alpha 3 1 2 plus 2 alpha 2 3 1 equals delta 3. Okay, so this is a linear system for 3 variables with 3 equations, so we can exactly solve this. And okay, the answer is just you sum these two guys, so you end up, and there might have been a 2 here, but that's it.
Yeah, if you look at the first line, there should be 2.
Yeah, that should be 2. Yeah.
Yeah.
And because you already factored these 2, so yeah. This is okay. This argument I just raised here that you asked. We pull out an extra factor of 2 in the lambda. Okay, and because it also has rotation, it also has pointer invariance. So everything must go with x1 squared, say. So we pull out this square factor. Okay, and this just cancels with this one. Okay. Do you want me to do this again? Okay, so we have 2 everywhere, so we can just. I know I'm not supposed to do this, but you guys get me. Okay. So you just sum up these 2 equations here, for example, have 2 times this guy, and you have this plus this, which is just delta 3 here from the last equation, equals delta 1 plus delta 2. And then we have that alpha 1, 2, 3 is just delta 1 plus delta 2 minus delta 3 over 2. Okay? And then you can do, I want to do this for alpha 2, 3, 1, alpha 3, 1, 2. But the final answer is that this guy on the point intersection becomes so when I put this back in, this 2 cancels this 2, okay, and I will also introduce that these people usually do this. Here they call the sum of all 3 scaling dimensions, delta 1 plus delta 2 plus delta 3 to be delta, and so this is just delta minus 2 delta 3 over 2, for example, okay? Just some shorthand. So this guy is like this, so we can compute it. Okay, remember the 2 cancels because of this. Then if you do the Same thing for 2, 3. You have delta minus 2 delta 1, and then x3, 1 you have delta minus 2 delta 2. Okay.
I missed the part where you erase the 2 from the alpha 1, 2, 3, 3,
Yes.
1, 2.
Okay, I started with this, right?
Yes.
And similar there. And then I introduced this here. Okay? You missed this part where I introduced this here. Okay, the reason is, okay. If I have this correlate, okay? And then I scale this guy. Okay? Then this, by scaling invariants, should be, in principle, this. That's what I wrote before. Okay? But this must also have point invariants. And point invariants will tell you that this guy must go like something like this. Okay? Actually, the difference with this guy another point. So because of these two factors from point invariants, we actually write this. Okay? We just separate what comes from point invariants to what we actually call scaling dimension, what is actually due to the field itself. Okay? And then I missed this factor here, and I originally wrote this equation. And then because of this, I just erased the two that are. Okay? Can I erase this? So just note that this delta here is the sum of all these deltas, those three deltas, which is different from this delta that appears on the 2-point correlation function. Okay? Just be careful. You see here that in the 3-point function, we still have an overall constant, C123. Okay? Since I normalized, remember, we had a constant here in the 2-point function, C12, which it chose to normalize to 1. Okay? Since we've done this on the 2-point function, we do not have the freedom to do this on the 3-point function. Okay? And so we're stuck with this constant. So the 2-point functions we were able to determine exactly with conformal symmetry. The 3-point function we're able to determine the functional form, meaning this power law behavior. We're not able to determine the overall constant depth. Okay? This C123, or more generally, if you have I, J, K here, or any scalar fields that might be present on your CFT, these guys are known as structure constants. Not in the sense of D group structure constant, just the same name, okay? They cannot be determined by this kinematical arguments alone, okay? Conformal symmetry alone is not enough to determine these guys, but if we have we need some dynamical information. Okay. And which kind of makes sense because it's a 3-point function, so it must naturally involve interactions in one way or another. Okay, and we're actually gonna see how this is done. This is the subject of the OPE. This is what the operated product expansion does for us. Okay, this is a topic for another lecture. Maybe in 2 lectures we'll come to this. So, but the message is we need dynamic information to determine these structure constants. Okay.
So is the interaction plot of the Lagrange enough to it or not? Because you mentioned interaction.
You might relate this structure constant to the coupling constants in your Lagrangian, but you're still not able to determine the actual value of the coupling constant or the structure constant. Okay, from the Lagrangian alone. Okay, you have to do this through the operator product expansion. Okay, this will furnish some non-trivial constraints on this structure constants.
Is there some restriction on the set of equations? So if either needed both scaling dimensions to be the same, so here is there some restrictions or is it
No, here the scaling dimensions are 3. Okay.
No,
They might all have different scaling dimensions.
But delta 1, delta 2, delta 3 can be completely different, or is there some restriction? Like
No, they can be different.
completely different. There's nothing that.
More questions? We're going to move to the 4-point function. Can I raise first blackboard? Okay, so same game. We have the most general rotational invariant correlator here for 4 points, 4 different scalar fields, again in principle. And again, already dropping the x1, x2, x3, x4 square terms because they were dropping the Fourier section because it wasn't the light. So you can already notice that something's different here. And it is that, again, just say the I scalar field has dimension, scaling dimension, that's all y. It can all be different in principle. And so this, on the left hand side, we furnished 4 equations. Okay, if you were to play the same game here. Okay, here the left hand side furnishes us these 3 equations. Okay, and this side here we got from analyzing the right hand side. But this time the right hand side has 6 unknowns. No. So you have two undetermined or just two free powers here. Okay? So you can already see that the 4-point correlator won't be as constrained as the 2-point correlator and the 3-point correlator. Okay? And another observation is, I'm just going to mention, but I'll come to this shortly, is that this constant here is not actually a constant anymore. It will be a function of two parameters, u and v, but I'll come to this shortly. Okay? But it's not a constant anymore. And I will define what is u and v in just a moment. Let's just want to focus on the denominator for now. Let's just view just write this linear relations here. If you do the same game there, you see that you have something like, if I did not make any mistakes on my notes, you have something like this. Okay, for equations, for 6 unknowns, A to F. Okay, so what do we do with this freedom? Here is we use this freedom to fix or to say guarantee or to factor out the scaling behavior of this correlator. Okay, this correlator must have scaling invariants. Okay. So what I'm going to do is actually, I'm going to, how do I write this? I'm going to factor this two powers here, which were A and C. And since I have two free parameters here, I'll choose A and C to be these two free parameters. And I'll use them to completely fix the scaling behavior of this correlation function. That means that I'll choose, I use this to choose A there appears with x1 and x2. So I'll just say it is delta 1 and delta 2. Okay? Doing the same thing I did for the 2-point functions and 3-point functions. Okay? And the other one is C. C. And I'll fix C to be delta 3, which is equal to delta 4. Okay? I could have chosen other parameters here, I could have put different factors here. It's just a choice, okay? I have freedom for this.
I mean, I understand why you can say that A and C are equal to delta 1 and delta 3. But why is delta 1 equals to delta 2?
Because if it was not, I wouldn't have a rotation invariant here. I wouldn't be able to have constructed this rotation invariant. Okay? It's the same argument that I gave on the 2-point function. When I said delta 1 must be equal to delta 2 in a 2-point function. It's the same reason. If I choose A to be delta 1 and C to be delta 3, okay, in order for this product, in order for me to be able to construct this quantity here, this guy, then A must be delta 2 as well. If it was a different power, then I wouldn't have this term here. Okay? It's the same argument. Yes?
I would say
Not satisfied? Anyone else not satisfied with this? Okay,
Satisfy the scale invariance. That's why you need delta 2.
With this.
Yeah.
Okay.
That's why you need delta 2, because if you scale phi 1, you need to get a delta 2. If you scale phi 2, you need to get the same delta.
Yeah, because if I cannot, then this, I wouldn't be able to construct this guy. I also have other sources here of x1, x2, but that's exactly what I'm getting to now when I go back to those equations there. Okay? Then again, the idea was just, I have freedom here. I have two free parameters. So I just use this freedom. Okay? And the reason is because I know this correlation function must be scale invariant. Okay? So that's what I'm doing. Using this freedom I have there to already take care of the scale invariance. Okay? And then we're gonna see what happens to this other part right now. Okay? But then again, I emphasize that this is a choice. I could have put, say, x23 here, x14 here. And then fix B and D, and so on. Okay? It is not the only way to do this. Okay? And this will have implications later on. Okay? This will lead to new constraints. Okay? Because since you can do this in more than one way, you see the ways that are different, but they should physically be the same. So this will furnish more constraints. Okay? You have any questions?
Yes. Sorry, I mean nothing had happened, no? What has happened? You've copied the same expression. What has happened? Sorry,
I just
this line.
no,
Well, I understand.
it's the same. The only thing I did, I just put these two guys here in front. Okay, just to emphasize. Okay, just a pedagogical step.
Okay.
Okay, nothing. Just to emphasize that I'm using the freedom on those two guys on the front. Okay, because the second part will become something else in a second. Okay, so let's plug this choice here on the system. So what happens is you see the this A will cancel this delta 1, it will also cancel this delta 2, and then C will cancel this delta 3, and will cancel this delta 4. So this system becomes D plus F equals 0, D plus E equals 0, D plus F equals 0, D plus E equals 0. And then this we can solve now. We have 4 equations and 4 unknowns. And let's say I use this last equation, so D equals minus E. And then I plug this in the first and second equations. So D is minus E. So this implies that E equals F. here, this implies that b equals minus z, but minus z is d, so b equals z. And then comparing these two equations, I get that b equals minus z. Give you a few seconds to check that out. Okay, I'm just determining d equals minus z, b equals minus z, and f equals z. Okay. I think that is correct. E equals minus b. Was that equals d equals? That is correct. So, what does this imply here? Well, this guy, his first factor is just x1, x2 will be delta 1, say, delta 2, doesn't matter. This guy will be delta 3, say. Now, this guy here, I'm going to put a square bracket like that. We have that b equals z. So let's put these guys together here. x2, x3, x1, x4. This has say b, okay, have the same power, and these guys have the same power, okay, e equals f, okay. So this is x2, x4, x1, x3. Okay, so this would be, say, E, but E equals minus B. Okay, so this is actually minus B. Okay? Now we just do one sneaky thing here. I'll multiply this by x1, x2, x3, x4. Okay, I'll multiply and divide by this. Okay. Okay, so what happens? Okay, I'm just multiplying by 1. So, and I forgot here the structure constant. So this is going to become I'm just doing this computation detail because it is not usually done in detail. Okay, they just give you the answer. And the reason is because it's just boring. Since this the 4-point function is one of the most important objects, so I chose to do this in detail here. So this guy here has x1, x2, x3, x4, b. I'll put it here in the first one, and this guy here has minus b, so I'll put here in the numerator with minus b. And so I have These are scalars, okay? It's made up only from scalar products, okay? Two scalars, U and V. And then if I just go to the point of section, just for completion, now I know what to expect. This product here will become x1, 2, 2 delta 1, x 3, 4, 2 delta 3. I'm just here. And then this guy will become something similar, which I'll call lowercase v and lowercase u. Just for space. So I have a v. U, the power of minus b, power of b, and c. Okay.
C depends on U and V. The same.
Yeah, and I'll get to why it depends on these two guys. But forget this for just a minute. Everything is